data analysis. And basically, a Snakemake workflow is defined in terms of rules, and these rules will represent all the different steps of your data analysis. And the way these rules are described is using a human-readable Python-based language. And on top of these rules, you can also add more description about the required software environment. And this is done using integration with the Conda package manager and container virtualization. The reason the Conda package manager is used is that this tool was developed mainly for the bioinformatics community, and this community rely a lot on Conda. And you will see also in the way the Snakemake workflow are defined that it's heavily influenced by the way the bioinformatics community is working, meaning that you basically define your rules in terms of files, and one tool will produce some files that will then be used by another tool, and this is very common in bioinformatics. And you will see that this is the reason why Snakemake is used a lot in this community. However, there is nothing about the tool in itself that cannot be easily extended to any other type of scientific workflow. So even if it's very popular in the bioinformatics community, it's not limited. The application of Snakemake is not limited to this field. On top of that, this is the scalable part. You can define your workflow as to be independent on the available resource and computing platform. So to define a workflow, you define it in terms of rules. Okay, and these rules describe how to get an output file from an input file. So here is a very simple rules, and it's start with the keyword rules, and then you can give a name to these rules. So in this case, I give the name example, and then you define an input and an output, and a path to the input file as well as the output file that should be produced. And in addition, you have a shell command. So this is the shell command that will be executed in order to produce the output from the input file, okay? And the dependencies between the rules are determined automatically by Snakemake by creating a direct acyclic graphs of the different jobs that need to be executed in order to produce the final output. Okay, so basically the different input and output will define the dependencies between the different rules, meaning the different job steps, and Snakemake will do all of that for you. And what we will do for the first part of this talk is going to a Python notebook, which basically describe how to write a workflow using Snakemake, and some of the most important part of the language of Snakemake. So, and for that, we will use a very simple workflow that will basically test if a book follows the zip flow, which is an empirical law which states that given a large sample of words, okay, in a text, the frequency of any word is inversely proportional to its rank in the frequency table. Basically, this workflow, the fact that we use this check of the zip flow is not very important. It's just a support, a dummy workflow in order to present the tool. Okay, and to check if indeed a text or a book follow the zip flow, we will define 3 basic rules. Okay, the first one that will be named count words, and that will take a book, okay, and just tokenize it and count the number of time a word is present in the book, and then we use we define a second rules that we will call fit zips that will try to fit the data to check if indeed it follows the zip flow. And then we have a final step, which is the plot zip that will generate a graph from the generated data. Okay. And what we will do is define these 3 rules in a file that we will name snakefile. If you are familiar with GNU-make, this is exactly the same. Snakemake is heavily influenced by make. And instead of a make file, you define a snake file, okay? And this file will provide the workflow description to Snakemake. So this is the example of our snake file. Okay, so we define the first rule, count words, that will look for a book that is called ISOL, and that is present in the books directory with name isol.txt. Okay, and it will, the output will be written to isol.dat. Okay, and for executing this job, we will use a shell command that we call a Python script, and we provide the input and output file. And then we have the second rules that do the fitting, and that will use the data generated in the previous steps, okay, here as input, and then provide the data that has been fitted using a second script. And then you have the final script that will use the two file generated at the previous steps, and then plot it and produce an image that will be called isol.png. And note that in this case, the final result, that is plot zip, is the first rule, because by default, Snakemake will execute the first rule in the snake file. And as this is our target in this case, it should be defined as the first rules. Should be noted also that the paths to the file are defined relative to the current working directory. Okay. So if we want to check the validity of a workflow, we can first perform a dry run. This can be done by passing the -n option when invoking Snakemake. So you have Snakemake. This is done just for the purpose of this notebook. So be sure that every time I run the command, basically everything will be run again. And here we do a dry run. So let's write the snake file and then execute a workflow using a dry run. And so what it did is say that it built the acyclic graph of the jobs, and you see that each rules will be executed one time. We have a total of 3 job steps, and then you have a summary of the jobs that will be run. So each of these jobs, in order they will be run. As you can see, count words is the first, of course, because this is the first step in your workflow. Then we have the fit and the plotting. What we can do also on top of that is print the shell command that will be executed by Snakemake. And to that, we can use the -p option. And you can see that indeed we have a print of the command that will be executed. Another thing we can do to check the validity of our workflow is visualize the direct acyclic graph. And for that, we can use the DAG option, --DAG, and then pass it to the dot command in order to produce an image. Damien presented the tool yesterday, so it's exactly the same idea. And if we execute it, we can see that we have a plot of our workflow. So with this box representing the different rules that will be executed, and the arrows between these different boxes is a representation of the dependencies between these different rules. So the final one, of course, depends first of the count words rules and the fit zip, while these rules only depend on the first job step, which is count words. Okay, so now if we want to actually execute a workflow, because so far using the --DAG or the -n option, we only do a dry run. In what we do is execute Snakemake, and then we provide an option, which is the number of cores that should be used. Snakemake, if the rules have no dependencies, if you provide multiple cores to Snakemake, can run these rules in parallel, so that it allows you to scale your workflow easily. And of course, this is what we will do. So we run it. we get a similar output of what we had previously when doing a dry run. Okay, so you see that you have Snakemake in the output say that you use one course, and then we have the different job steps that execute. And if we go to the output directory, indeed, we have the different files that have been created. And we can also visualize, in this case, in the notebook, the final result, meaning the image of the plot. And we can see that the book we use kind of follow the zip flow. So we obtain, when doing a log-log graph, kind of a straight line. Of course, in this case, we use the force all in order to run all the jobs, but in actual production run, you will not do that. And if the output of a rule is already existing, Snakemake will of course not run the jobs that generate it. And in general, if you want to know when a job will be executed, it will be executed if the output file, of course, does not exist, or if the output file needed by another jobs does not exist. It's also check the stamp, the date and time, and of course, if the input file is newer than the output file, then a new output file will be generated. And if input file will be updated by other jobs. And of course, as I said, if you use the force all, then it means that all the different step of your jobs will be forced to execute even if a file already exists. So for example, here, if we remove the final result of our previous run and then run Snakemake again, what we see is that only the plot zip job is run, and the reason for that is because, of course, the previous step has already been run, and we already have the input file, meaning isol.dat and isol.feed.dat are already present on the file system, and we don't need to run the job again. You can also provide the output file that you want to generate, and then Snakemake will execute only to produce this output file. So in this case, if we just want the fitting data, you can see that we have only two job steps that will be run and not the final one, meaning the plot step. And the reason for that is that we specify to Snakemake that we want only the output /isol.feed.dat, and of course it just runs the jobs that are required to produce this file. Now, if we look at our workflow, we have a lot of paths that are hard-coded inside of it, which make it very difficult to modify if we, for example, change the title of the books or anything. So it will be very difficult to maintain in the long run. So we have to modify it a little bit in order to make it more readable first, and also more flexible. So first, what we can do is replace the input and output specification in the shell command using a curly brace syntax. And basically, this syntax is using the Python format mini language, which means that if we use this curly brace with input or this curly brace syntax with output, then it will be replaced by Snakemake as the actual name of the input and output. So for example, if we have multiple inputs, okay, we have a list of inputs, file 1 and file 2, then we can, instead of just specifying this file in the shell command, we can simply use the curly brace input and curly brace syntax, okay? And then this will be replaced by Snakemake and will be evaluated as pass to file 1, pass to file 2. It will remove the comma here in order to avoid any problem, because of course most of the time in shell command you don't have a comma between different inputs. What you can do also when you have multiple files like this is that you can access it using an RS syntax. So in this case, input 1 and 2 can be accessed using an array syntax with providing an index. What you can do also is name your input, and then you can access it using a dot. And so for file 1 and file 2 will be accessed as input.file1 and input.file2. What we have also in our workflow is that for every rule we repeat the name of the book, which is kind of unnecessary because Snakemake can make that for us, so determine the name of the books automatically. So what we can do is use what is called wildcard, and this is defined in the input and output using, again, the curly brace syntax, okay? And then we can completely rewrite the count words rules using first that we here a wildcard and then replacing input and output in the shell command. So this is how our workflow will look like, okay? So we use all the little trick I explained before. So here, because we have two inputs to make it more readable and understand which part, which input correspond to what, I use some name for the input, and then I access it using the input.wordCount and input.fitting in the shell commands. And here I replace the name of the book with a wildcard. And because when this rule will be run, Snakemake will see that it needs a file called in the outputs directory that is called isol.dat, and then it will look in the other rules and see if it is possible to replace one of the wildcards with isol in order to indeed produce the file needed for the plot zip through. So because we specify the name here, we don't need to specify it for the other rules, because this will be replaced automatically by Snakemake. So indeed, I need to up. That's better. So what we can see here is that we have a new element that is present in the box describing the rules, and basically this is indication by Snakemake of how it replace the wildcard. So in this case, it's said that the wildcard book is replaced by ISO. Okay, and we can again run our workflow, and the result you can see when we print the command that indeed in every comment Snakemake replace the wildcard with the appropriate name. So this is very interesting because we basically only need to define the book that is the target on the first rule, named plot zip, but we don't need to define it for the other rules. Okay. And one of the advantages, of course, of using wildcard is that we can quickly extend our workflow to include more books. And for that, we will use the fact that Snakemake is basically Python code, and it means that we can include arbitrary Python code inside of our workflow. And for example, we will define a list with all the name of the books that we want to analyze. Okay, and then we create another list from this list, doing some substitution and using list comprehension. So we will define the final result that we want to obtain. Okay, and we say, okay, I want all these plots, and for that we use Python format, and we substitute book with all the books present in the previous list that we defined. And then we define another rules that we will call rule alls, and we define another rules that we will call rule alls, and we say that these rules should take as inputs all the plots that we define before. And so Snakemake knows that we want to, this is the final result that we want to obtain. An alternative is to use the expand function that is provided by Snakemake, and that allow you to have a very short alternative to the list comprehension that we use in this case. So we just say that we want to expand a book using the list books. So this is how the workflow looks like. So we define all the books that we want to do, and we use the expand function in order to produce all the plots. So the final result that we want to produce. And then we have the rules are as defined before. And then we use the rule all in order to specify to Snakemake that we want all these final result, meaning all these PNG files. And because all the PNG files are input for the rule alls, it means that they are dependencies of this rule. And so Snakemake will also execute the plot zip function and replace the book wildcard here in order to produce these plots, because it knows that it should generate a PNG file here. So if we look at what our workflow looks like now, yeah, first I have to write the snake file. So it looks like this now. We have all these rules that will be executed, and basically we multiply our workflow by 4 blocks. And here we can see that the different wildcard for books, so ISOL, Abyss, Last, Sierra, meaning the books that we define in this list. What you can do also with Snakemake is not only run shell command, you can also directly use a Python script. And for that, we define a new rules that we call aggregates. And these aggregates rules basically will take all the files that the dat file and aggregate them into one file. And instead of using a shell command here, we use a script. Okay, and script is defined in aggregate.py, and in aggregate.py what you can see is that we use an object called Snakemake, and basically this object allows you inside of the script to access data that are defined in the rules. Okay, so instead of shell, you use scripts, and using this script, you can define another script that can access the data in the rules using this Snakemake object. And in this case, I access all the inputs using snakemake.input, and also for the output file, I access it using the Snakemake object, then using a dot and then output. So basically everything that you define in the rule is accessible to the script through these Snakemake objects. And so this is the new workflow using these aggregate rules. And instead of using shell command as we did before, we use a script, and inside of this script we can manipulate the Snakemake objects in order to query information about the rules that we are running in. Note also that Snakemake is not limited to Python scripts. It can be used with R, Julia, or Rust. And the same thing using a script. And for all of these language, there is also a Python, an object, a Snakemake object that is defined so that you can actually access information about your rules. And so query information, and from this information, run your data analysis. What you can do also is separate your workflow from the actual data that you are using, for example, a config file. And in this case, I define a file that is called config.yaml. And inside of this YAML file, I define two things. First, the books dir, so the directory where the book is stored, and the output dirs, which is outputs. And in the snake file, I define the config file and say that it should read config.yaml. And then Snakemake will read this configuration file, and then this configuration is accessible through a dictionary that you can use inside of your snake file. So in this case, from this configuration, we have book dirs and output dirs. You can access it through the config directory that is, and then use simply the name of the label we put in the YAML file. And then we use these variables to define other variables that will be used in the input and output directive of our workflow. And basically, we use Python formatted string in order to replace book dirs, output dirs inside of these variables. And note that because we want to preserve the book wildcard so that it can be used by Snakemake, in this case we use double curly brace that will be then expanded as a single curly brace, but they will be defined as a wildcard for Snakemake. What we can do also, so in our previous workflow, what we did is every time define the books, but of course this is hard-coded in our workflow, so it's not really practical. So what we want to do is become independent of that. So what we do is use the glob wildcards functions in order to do file globbing and extract the name of the books directly from the file system. Okay. So what I did there is first using string formatting in Python is replace the books dir by the actual books dir defined in the configuration. And then I have this wildcard that is the book. And the glob wildcard function will output name tuple. And then I can basically access the names of the books present in the books directory using .book on the result of the glob wildcard function. So this is how our final workflow looks. So let's go through it because it's basically all the different steps that I described put together. So first we have a config file that I already written, okay, and then extract the configuration from the config directory created by Snakemake. Then I create different variables that will be used to define the books, the dat file that will be generated, and the book fit file description. And then I use the glob wildcard in order to extract all the books present in the book directory from the file systems. And then I define all the different arrays of files that should be generated. And then I have my actual workflow. So what I use here is that I want to produce all the plots, so the BNG files, and for the aggregated data as well, meaning the result for all the books. So taking all the result from the dat file from all the books and aggregate them into one file. So this is basically our final workflow. Okay, if you want more information about Snakemake, there is some links inside of the notebook that is, and the link to the GitHub repo containing the notebook is on the Indigo website. And if you want also, you can run this notebook using Binder and so that you don't need to install all the different dependencies. You can directly test it in your browser using this link. And again, this link is also present on the Indigo website. Okay, so no questions so far. Okay. Next step in our discussion of Snakemake is reproducibility. And one of the way, yes, Olivier?
Yeah, I just have a questions about the aggregate.py, so that script stuff. So it's override the scripts by replacing those inputs and then execute that as a script, or is it you need to have some import at the beginning to have access to the object? Or?
No, you have nothing. So this is basically the full script.
Mm-hmm.
And you have nothing to do. Snakemake will do everything for you. So you don't need to import anything in the script in order to have access to this Snakemake object.
Okay. So in itself, this code cannot be run directly in the normal Python stuff, right?
Oh no, it will crash for sure. Yeah.
Okay, thank you.
Yeah. Okay. Yes, it's directly linked to the workflow. Yes. So for reproducibility, you can use containers, and this is directly integrated by Snakemake. This can be achieved on a per rule basis, where you can specify containers to use using the container directive. So here I have again my example rule, and this example rule define containers that should be used in order to access some tools that will then be used. You can use it with script or shell. When you use containers, you have the choice. And basically these containers is a Docker URL that will then be pulled by Snakemake and run with Singularity. But you have the choice to use these containers. If the tool is already installed on your system, then you can decide that you don't want to use the containers defined in the rules. And so what it means is that you have to explicitly request your rule to be run with Singularity. It means that on the Snakemake command line, when you launch Snakemake, you have to specify that you want to use Singularity. And these containers URL, you can use anything that is supported by Singularity. So by the pull command of Singularity. So you can use, for example, Docker or Singularity Hub. The developer of Snakemake recommend to use Docker because they plan to support Podman in the future, and so it ensures that your workflow is portable and can be used with multiple containers runtime. So in the previous example, it was a containers that was used only for one rule. You can also decide that you want to use a global containers that will be used for your entire workflow. But of course, it's not always desirable. In some cases, you may not want some of the rules to run within the containers. And in that case, you have to define indeed that the containers directive, but instead of providing a path to the file, to a container image, you simply specify that it should be none, which means that for these rules, no containers will be used. But for all the other rules, the global containers will be used, and the rules will be run within this container. For reproducibility, and so make sure that all the tools needed by your workflow are installed, you can also use Conda. Of course, it depends on the policy of your local HPC center. Most of the HPC center don't really like Conda because it uses a lot of files, generate a lot of files, and of course the number of inode on the file system is limited, and so some of the HPC center don't really like Conda, so you have to check if indeed it's okay to use Conda on your cluster. And to define a Conda environment, you use the Conda directive, and then you pass a path to a file, a YAML file that define your Conda environment. And this is here in the example. Okay, I say that I want to use an environment defined by hence mytools.yaml, and in this file I specify the channels to use. So in this case, Conda Forge, and then as a dependency, so meaning the tools to install, I specify what I want Conda to install. And optionally, of course, I can omit it, but you can specify the version of the tools that you want to use. And as with containers, you have to explicitly specify to Snakemake that you want to use Conda, and that Snakemake should create the Conda environment. So in this case, the option to enable Conda is use the use Conda option, -- use Conda. In some cases, you may run into a problem if you try to create the Conda environment on the compute node, if you were running Snakemake on a compute node. And the problem may be that you don't have internet access, and then, of course, the creation of the Conda environment will fail. You have a solution for that, is that on the login node, you can create the Conda environment using the Conda create ends only. It will not run the workflow, but it will just create the Conda environment, and then once this Conda environment is created, you don't need to create it again when you run your workflow on a compute node or somewhere where you don't have internet access. What you can do, of course, is combine Conda and containers. And for example, you can just use the mini Conda containers that will be used as the Conda installation for your workflow. And so you define a global container, okay, with mini Conda. And then you can define your environment using the Conda directive and an additional file, YAML file, describing the Conda environment that you want to use. And in that case, of course, if you want to run this workflow, you need to use the use Conda as well as the use singularity option. What you can do also is to use environment module. This can be done using the env module directive, and then you provide a list of the modules to be loaded into the environment when the rule is executed. And again, as with Conda and containers, you have to explicitly specify that you want to use environment module using the -- use env modules option. What you can do, of course, is define for a given rules, the containers, Conda environments, or environment modules, and depending on where you are running, use one or the other. You have multiple options. For example, you define a containers and a Conda environment, and then depending on the option you activate in the command line, either use Conda or use Singularity, you will use the Conda environment that will be created, or the containers. And you can do the same with environment module, define, for example, a Conda environment and also environment modules, and activate it either using use Conda or use environment module. So depending on the option you pass to Snakemake, it will not use all the definition you put in the rules. And of course, it may be interesting to define both a Conda environment and the environment modules. If you want to send your workflow to someone else, because of course the name of the environment modules on an HPC cluster is really site dependent. Maybe if a site use EasyBuild, most of the time the naming scheme will be the same for all these sites, but of course it's not guaranteed. So using environment module is not really portable. You cannot use it everywhere. So defining multiple options, meaning a containers, environment module, or Conda, can be a good idea if you distribute your workflow so that the user that will use it at the end have the choice of the way he wants to use your workflow. Okay, now for the last topic is how to scale with Snakemake. One of the things you can do is define the number of threads that should be used for rules. So this is done using the threads directive. So here I define the rules that will use 8 threads. And when you define the number of threads, Snakemake will do something else, is also define some of the common environment variables that define the number of threads to use. So it will define OpenMP threads, it will define OpenBlastNum threads, MKNum threads, and so on. So this is, and by default, Snakemake will set all these values as 1 to avoid oversubscribing the system, but you can override it by using the threads directive. And these value can then be used in the shell command if you wish, using, again, as with input and output, the curly brace syntax. So the value of 8 there will be replaced in the shell command by Snakemake. One important thing is that I say that Snakemake should be independent on the actual system, is that the number of threads that you specify in your workflow may not be the number of threads that will be used when you run your workflow. When Snakemake is executed with fewer cores than the number of threads in the snake files, then the number of threads will be defined as the minimum between the value of threads and cores, meaning the number of cores that you provided in the command line when launching Snakemake. Okay, and so as we have seen with the demonstration in the notebook, you can define the number of cores to use using the -- core option. On top of that, you can also define some resources that will be used by your rules. And this is done using the resources directive. And Snakemake define 3 standard resources. In this case, I use 2, one of them, but you can define arbitrary resources depending on your workflow, and then use this value inside of it. But Snakemake use 3 standard one, which is mem _MB, which is the memory usage in megabyte, the disk usage in megabyte with disk _MB, and tmpdir, which is the temporary directory to use. And note that when you use, you specify a tmpdir inside of the resources, then Snakemake will automatically also define the tmpdir environment variable. So if you use the tmpdir environment variable in the shell command, then it's accessible because Snakemake will define it using the value you provided in the definition of the rules. And previously, we have seen that the number of threads to use can be constrained by the core option to the command line. And the same is true with the resources. You can specify here the resources, maximum resources to use as command line option. And to illustrate that, we will consider this very simple example. So we have a rules called sort, and it can use up to 4 threads. and we'll use 100 megabytes. And then we have a dummy command here sort in parallel with the number of threads, okay? But if we launch Snakemake with -- course equals to 2, of course, it's inferior to the value we provided there. And it means that Snakemake can basically run in parallel only one sort jobs using 2 threads. So it will not be 4 threads, it will be 2 threads because it is overwritten by the value we provide here. If we launch Snakemake with course 8, then Snakemake has the possibility, the Snakemake scheduler has the possibility to run 2 sort jobs in parallel using 4 threads each. Here, if we say, okay, Snakemake with 8 cores again, but we constrain the resource, meaning the memory, we constrain it to 100 megabytes, then even if we provide more cores, it cannot run 2 sort jobs. It can also only sort 1 because here we see that the resource is 100 megabytes. And again, we constrain it to 100 megabytes. So it means that 1 sort job can be run using 4 threads. Okay, in parallel, only 1 sort job. The default resource for the rules that do not define explicitly the resource can be provided also via the command line using the -- default resources, and then a list of the resources used by default by the rules. And you can also overwrite what is provided in the snake file using the set resources option. Now, of course, you can run Snakemake on a login node. If this is very small workflow, you can decide to allocate a node to Snakemake and basically run directly the Snakemake command inside of your bash script, or you can use it with Snakemake on the login node, but then submit all the job steps as individual jobs to a cluster. And Snakemake makes that Snakemake is designed so that it is relatively independent on the cluster it is running on. So it means it's independent of the scheduler. And to submit the jobs to the scheduler, you use the -- cluster option, and then you provide the name of the command to execute in order to submit the jobs to the job scheduler. So in our case, in a Slurm cluster, we will use sbatch. If you are on a PBS one, you will use qsub. And then you have to use -- jobs, and then an integer that defines the number of jobs that can be submitted at once by Snakemake. So if you have a very large workflow and you were limited by the number of jobs that you can run at the same time on your cluster, then you can define the limits of the number of jobs that Snakemake can submit at once. And this is done using this -- jobs option. And of course, you are not limited to just provide a command. You can also use a more elaborated command in order to submit the jobs to your cluster. When you submit the jobs here with Slurm, you can, of course, provide the sbatch commands, but then inside of the sbatch command, you can query information from Snakemake and define the resources needed by your jobs. So for example, if inside of the rules, there is the minimum time, as well memory or number of GPU or CPUs, sorry, that are indicated, then you can query these values and use them in order to create your Slurm jobs. And here for the outputs, I decide that I will put it in logs Slurm directory, and then I query the name of the rules as well as the wildcard in order to produce the name of the output file. So it's really flexible. So in itself, it's completely independent on the scheduler. This is the user that provide exactly the command to run in order to submit the jobs to the scheduler. Of course, when Snakemake is run on this mode, it will query quite a lot the scheduler to check if indeed the job is finished. And the problem is that if you request too many times to the job scheduler the status of your job, you may slow down the scheduler, and other user will be affected. So be careful when submitting a large workflow to using Snakemake. Make sure that first you don't submit too many jobs, meaning that you will reach the limit of jobs that is allowed for you, but also that you don't submit too many jobs at once. And not too fast. So there is two options. You can specify the max jobs per second that Snakemake should submit, and also the max status check per second, meaning the number of times per second that and the status of your jobs is checked by Snakemake. And of course, you don't need to provide integer there. It can be a fractional value. So if you have a job that you know that will run for about 10 minutes, of course, it's not really interesting for you to ask Snakemake to check the status of these jobs for every 1 second. It will just overload the scheduler. What you can just do is ask Snakemake to check the status of the job, I don't know, once every minute or something like that. What you can do also to define values that are specific on the cluster you are running on is using a profile. Because if you were running on a cluster on a very regular basis, and every time you launch a Snakemake, you have to provide all the command line options, it will be a pain in the ass for the long run. So it's possible to define a profile that specifies a configuration specific for the machine you are running on. And for that, you use a -- profile option, command line option, and then a profile name. If you provide just the name, then Snakemake will search for a folder named profile-name, for example, in the user global configuration directory that is in your home directory .config/snakemake. But you can also provide an absolute or relative path to a directory. And inside of this directory, Snakemake is expect to find a file that is named config.yaml. Okay, so this is an example of using a profile. So you run Snakemake and you say that in the current directory there is a directory named profile, and inside of this directory you have the config.yaml file. And basically the way you write this YAML file is that every option that is -- some option become some option. So you remove the dash, the double dash at the beginning, and you just write along the value that should be used for this profile. Here there is a link to different profiles that have been created by other, and that contains a default profile for PBS cluster, Slurm cluster, and different information about this profile. So if you want some example of Snakemake profile, then you can look into these repositories that are in the link I provided there. So example here, I said that the default resources should always be 1 gigabyte, and that we should not use a Conda, but use Singularity every time. So this is a way to avoid to write all the command line option every time you run a Snakemake. This is a more complex profile, where we also provide all the information in order to submit to the cluster. So we have the cluster command that is replaced by creating a directory for the log file of Slurm, and then we set the CPU per task to threads and so on, as well as creating some structure for the output file that should be created. And we say that we should run maximum 10 concurrent jobs. And here I provide also a default job script. And this is done so that I can add additional information in the job script that will be used by Snakemake to submit the job. So this is a basic job script. So in this case, you should not touch the property equals property. This is used by Snakemake as well as exec job. So these two parts is just used by Snakemake, but there in the middle, you can introduce everything you want. So for example, if you are using a Singularity and you want to bind additional directories, then you can export the Singularity bind environment variables and add, for example, a TMP dir, but maybe you want to add the scratch if it's not defined by a TMP dir, or you want to mount some of the MPI libraries depending on the container you have. So basically, these allow you to add additional information inside of the bash script that will be submitted by Snakemake. And so you do that by providing a job script. Of course, you can also do the same using the -- job script command line option instead of a profile. So to wrap up, Snakemake is a workflow manager that offers a very simple Python-like syntax with high readability and flexibility. It's really flexible because you can, using the wildcard syntax as well as some provided command by Snakemake, really create a complex workflow with just a few rules, and then everything will be inferred by Snakemake automatically from the wildcard you have provided. It allows the easy mixing of shell commands and high-level language scripts. So Python, this is the only example we have discussed today, but you can also use Julia, R, and Rust. It ensures reproducibility and dependencies management of the workflow. First on using the Conda package manager or using containers or a combination of the two. And it also provides a mechanism to manage the resource and cluster execution. And if you want more information about Snakemake, there is here the link to the website and the documentation.